3.3 kind of builds on what we started in 3.1 when we were working with the derivative and talking about critical values. This is called increasing, decreasing, and then the culmination is something called the first derivative test, okay? And we'll get to actually see what that is today. So if a graph exists on an interval, first of all, what is an interval? When we say an interval, are we talking about an x interval or a y interval by default? Because it doesn't say here. An x interval, right. We look at the independent variable. So as we look at a graph from left to right, between two x values on the real number line, so there's infinitely many points on any x interval. If a graph exists on an interval, it's doing one of these three things, and only one of these three things. It's either increasing if your y values are getting bigger, it's decreasing if your y values are getting smaller, and it's staying constant if your y values stay the same. Okay, that's it. Because the first derivative tells us what the slopes of the tangent lines are doing, then if we know the sign of f prime on any given interval, we will know then if the function is increasing, decreasing, or staying the same. Okay, just the sign of f prime gives us that. The magnitude of f prime tells us how fast it's increasing. So here we go. Let's say we have an interval from a to b. This is an open interval. This is an if and only if statement. If the function is increasing, that means it's going up from left to right, then we know the derivative on that interval is positive. The other way around, if we know the derivative is positive on the interval, we know the function's increasing on that interval. Similarly, with an open interval where f is decreasing, that means the derivative is negative. If the derivative is negative on that interval, then the function is decreasing. And to be boring like this, if on an interval the derivative is 0, we know the function's constant on that interval and vice versa. Okay? So it's just the sign of f prime that tells us that information. So what we're going to do is we're going to be looking at open intervals, open x intervals, where the function is going uphill from left to right, downhill from left to right, or staying the same from left to right. So here's a graph of a function from -3 to 5. It's always nice to start off with the graph because it's the easiest way to answer the questions. We want to know for this function f of x, on what open x intervals is the function increasing, decreasing, and constant. So increasing. Is it increasing from 5 to -3? Do we read a graph from right to left? No, no. Okay, so here's the part I see that's going uphill. Would we then say it's increasing from -2 to 2? No. Those are y values, right? The y values increase from -2 to 2, but it's because those y values are increasing, we want to know the x values for which that occurs, which is from where to where? -3 to 1. Yeah, good. So you can list it like this. And that looks like an ordered pair, right? But we know it's not because context clues, right? We can read the context. This function is decreasing when the graph's going downhill. That's from 3 to 5. Now, if you want to clarify, because it does look like an ordered pair, you could actually, same thing you would do if you were listing something as a max. You could clarify by saying absolute max or global max. If you're talking about an x interval and it looks like an ordered pair, you can stick like an x epsilon in front of it. And now that just clarifies that it is an x interval. But it's not needed. It should be implied to be an x interval. And the function is constant on the interval from 1 to 3. Yeah, on the interval from 1 to 3. Piece of cake. Easy, right? So that was a function that did a little bit of everything. Rather interesting. What type of equation would give us the graph of this function? Piecewise function. Yeah, this would be a piecewise function. So typically, if we have a graph that's generated by a single function, it's not going to have horizontal intervals unless it's a horizontal line. But before we move on, if a function is increasing or decreasing or constant on a specific interval, we say it's said to be monotonic increasing, monotonic constant, or monotonic decreasing on that interval. The word strictly can be used interchangeably with monotonic. So something that's monotonic increasing on an interval is equivalently said to be strictly increasing on the interval. All right, here's an important idea. If f is a continuous function, continuity is a very important property of many functions, then f prime can only change its sign at a certain location. Here's some examples. We're looking for f prime to change sign. So here's where f prime goes from positive to negative, negative to positive, or it could be like that or like that. For a continuous function, a function can only go from increasing to decreasing or decreasing to increasing at a specific type of x value. What are those types of x values? Very good. Bless you. In the start of this section or this chapter, we define those to be critical values. So for a continuous function, if we can find the critical values, those are the possible locations where the sign of f prime changes sign. Is the sign guaranteed of f prime to change at a critical value? No. You could have something like x cubed. It comes in from the bottom and goes horizontal right there, and you may be thinking that it's going to go down, but all of a sudden it goes psych, and it goes up. That's a critical value, but it's not a sign change in f prime. F prime is positive on both sides, so that's not going to be a sign change. But if it is continuous and it does change signs on f prime, it's going to be at a critical value. Now, for a non-continuous function or a discontinuous function, the sign of f prime can certainly change at a critical value, but it can also change at another location. For instance, if we have this right here, there's your x value, or it could be something like this. Look like that. Are these critical values of a function? No. Why could these places where we have our jump and the vertical asymptote not be critical values? Yeah, the function doesn't exist. And critical values, first and foremost, have to be in the domain of the function. But can the graph change from increasing to decreasing or decreasing to increasing there? Yeah, obviously it does, right? The one on the left goes from increasing to decreasing. So f prime changed from positive to negative. Similarly on the next one, f prime changed from positive to negative. Now, keep this in mind, too, that just because it's a discontinuity doesn't mean it can be a critical value, because I could just as easily fill in like one of those dots or put the function value somewhere else by defining it explicitly by a piecewise function. Those now would be critical values. But for a discontinuity where the function is also not defined, we have to be on the lookout for those as well, if we're interested in finding the intervals where a function is going up or down. Okay, so if a discontinuous function, then f prime can change its sign either at a critical value or at a discontinuity. Okay, keep that in mind. All right, so once we have those small types of x values, or categorically it's small, right? There's only two types, critical values or discontinuities. That means that in between those values of x, the function has to be monotonic increasing, monotonic decreasing, or monotonic constant. So we can then essentially test the intervals in between those critical values or discontinuities, and we should be able to determine then from that if our function is increasing, decreasing, where. So let's try it out on example 2. It says to find the open intervals. That means open x intervals or y intervals? Yeah, good, x. Open x intervals on which this cubic polynomial is increasing and or decreasing. Notice it doesn't say constant. Okay. And then it says to justify. Sweet. All right, first things first. Is this function continuous or discontinuous? Bless you. It's continuous, right? So the only values of x where this can change its increasing, decreasing behavior is at a critical value. Let's find the critical values. We'll take the derivative, and we get 3x squared minus 3x. On the key on the notes, you'll see me always doing this. F prime equals dne. We want to at least consider it, and in this case, it never happens. If you know that you're not going to get any critical values from that, you don't even have to show this, okay? As long as you've considered it first in your head, you don't have to show that. So it must be then where the derivative is equal to 0, and you could show me that by either setting f prime equal to 0 or setting the expression that is f prime equal to 0. Either one of those is going to earn a check. You always have to show the equation that you're solving. And once it's equal to 0, then our goal is to f it, right. And the first rule of effing it is to factor out a common factor. And we have a 3x that's common, keeping it equal to 0. Now from here, you could just rattle off the critical values. X equals 0, x equals 1. These are the CVs. We don't even have to check to see if they're in an open interval because we're not doing the MVT. We want all the critical values for the function. It has 2 of them. So if these are the only places where the derivative then, through a continuum, can change its sign, and I want to know where it's increasing, decreasing, we're going to make a number line chart. Number line charts before 2008 were very important on the AP exam because they were part of what the College Board was looking for as justification on the free response. But since 2008, College Board does not acknowledge number line charts for final answers or justification. But there's still a both fine and dandy way for you to collect your information so you can answer the question correctly. Here's what we're going to do to make a number line chart. First, draw a number line. And I would prefer a horizontal number line instead of a vertical since we're talking about X values. Makes sense. And then somewhere from the left here, put 2 bars. We're going to turn this number line essentially into a table or a chart. On the top row, we're going to have X, and on the bottom row, we're going to have F prime. Then we're going to come to the number line, and we're going to put our critical values down in numerical order. That's how number lines work. So instead of putting just a little small tick at 0 and a small tick at 1, because we're going to make it look more like a chart, make them kind of a tall line and a tall line. And at the top there, put the critical values, 0 and 1. So those lines are now tall so they can define the rows, but they're also elevating the critical values. Now when we say X and F prime, bless you, what we really mean is we're picking a test value of X, and we are only interested in the sign of F prime. You don't have to write test and sign though. What we can do then now is pick any value of X to the left of 0. Because the sign of F prime should be the same everywhere to the left of 0. Any value less than 0 would work. -1, I heard, that's a good one. You're going to want to keep them kind of manageable. We then pick a number between 0 and 1. 1/2, and then a value to the right of 1, 200. Good. That should work. Now notice where I wrote those. I wrote those on the number line, lower than the critical values. The critical values are still staying prominently written up above. Now I just got to figure out the sign of F prime. So if we come back up here, we have 2 versions of F prime. We have 3x squared minus 3x, and we have 3x times x minus 1. If we are only interested in the sign of F prime and not the magnitude, which of those would be easier to obtain the sign from? The expanded or the factored? The expanded. Okay, let's plug in the 1/2 into the expanded one. 1/2 squared is 1/4 times 3 is yuck. Yuck, that was the wrong answer. Okay? If you're only interested in the sign, you want to plug your numbers into the full-fledged factored form of F prime. The full-fledged factored form of F prime. What do I mean by full-fledged? I mean, if in the process of solving, you divide, let's say, through by a 3 or a -3 would even be more important, you don't want to use that version. This is the entire derivative fully intact. You go back to the factored version of a fully intact derivative, and it's a lot easier to determine the sign because you're just evaluating much smaller expressions, and of course you know what the product of 2 types of numbers is. So let's try the -1. If I plug in a -1 into the full-fledged factored form, I get -3, which is negative, times -1 minus 1, which is negative. What's a negative times a negative? Positive. So down here, I'm just going to put a plus sign. Or you can write the word positive. Darn lunch. Okay. Have a good lunch. We'll finish this when you get back.